Our next speaker is Ralf Jung. He is an assistant professor at ETH Zurich, learned Rust 10 years ago, got into the Rust project by working on Miri as part of a Mozilla internship, and I'm told maybe a master plan, a secret master plan, 8 years ago, and is now a maintainer of Miri and a co-lead of the OpSem team. And he's going to talk to us about MiniRust, a core language for specifying Rust. Please make him welcome.
Yes, great. Mike is also working. Yes, thanks a lot for the introduction and thanks all for coming. I didn't think I would ever give a talk about formal semantics in front of a packed movie theater, so this is great. Though there have probably been more exciting movies played in this room, but fair enough. Okay, so specifying program semantics. Turns out that's a hard problem. And to demonstrate why that's a hard problem, I want to show you a little example. So here we have a little bit of Rust code. There's some unsafe in there, but there's a safety comment, so don't worry about it. And so we get an integer from somewhere, and then we just test something very innocent on the integer, because I called my mathematician friend, and they told me that every integer is less than 0, or equal to 0, or greater than 0. And so clearly, that should be true here as well. So we can just go ahead and run this code, if I find the right browser window. And we run this code in the latest stable compiler. And maybe I need to make this bigger or maybe not with this screen. And it turns out that the assertion fails, as you can see here on the right, which is a bit strange. I guess now I need to call my mathematician friend and tell them we discovered a new integer. We don't yet know what it is, though. So let's figure out what the integer is. And let's just add a print here so that the compiler tells us what the strand integer is. And it turns out the strand integer is 0. And also, if we look at it, the error goes away. So maybe I need to call my physicist friend instead, because this is clearly some sort of quantum thing, right? So, okay, what the heck is going on here? And by the way, if you try the latest beta that will be stable tomorrow, same thing. So what is even going on here? Well, there's kind of two options of what could happen here. This could be undefined behavior, which is like when you're breaking the rules of what you're allowed to do in unsafe code or not. And as we all know, with undefined behavior, everything is possible. So there's always a possible answer. But of course, it could also just be a plain old compiler bug, right? Like, who knows if the compiler is actually doing the right thing on this program? And so how do we find this out? Well, we go read the specification, and it should tell us. So oh, yes, there is no specification. That is in part why I'm standing here and giving this talk, because I have some opinions on how the specification should look like. But we're kind of stuck here on the Rust side. So let's do the same thing again, but using a different programming language. So this is basically the same program, now written in C. And we can do the same thing again. We go to the demo, and it opens in the browser, hopefully. And we take the latest Clang compiler, and again, Clang also discovered a new integer. I had to make it a little bit more complicated here to trick Clang into doing the right thing, or the wrong thing. But in the end, you can see that also here, something really weird happens. And so, same game as before. This might be UB, or this might be a compiler bug. And this time, we can go read the standard and find out, because C has an extensive standard. So let's do that. So here's the program again, kind of crammed into 4 lines. And so let's see what we can find in the standard that might be relevant to this program. So first of all, we find somewhere in section 6 that where we just have a local variable and we don't initialize it ourselves, the initial representation of the object is indeterminate. Okay, now we have to figure out what is going on with indeterminate representations. Section 3 tells us an indeterminate representation is an object representation that either represents an unspecified object or a non-value representation. Okay, so we have 2 more words we have to figure out what those mean. So if we go search for non-value representation, there's somewhere, we are back in section 6 now, but different part of section 6, where, well, certain object representations do not represent a value of the type. And if we do something with them with an L-value expression, that's what we call a place expression in Rust, that does not have character type, then something, something, something. Also, such a representation is called a non-value representation. So in our case, our L-value expression has a character type. It's not an accident I used signed car here. So this shouldn't apply to us, right? This can't really be a non-value representation in that case, hopefully. Though we can also go look for more hints of whether there could be a non-value representation or not. And somewhere else in section 6, we find that, first of all, signed car does not have any padding bits. And we also find, as a non-normative note, but still potentially useful in interpreting the standard, that one way to get non-value representations is to have some sort of wrong padding in integers, because like some machines have integers with like parity bits or something like that. So this is how you could get a non-value representation. But sidecar doesn't have any padding bytes. So like hopefully, I guess maybe it doesn't have non-value representations. So let's just assume it doesn't. So the other thing that it could be is an unspecified value. And what the standard says about unspecified values is, well, that we have a bug, and also that it is a valid value of the relevant type where this document imposes no requirements. And I mean, surely there's no valid value of that type which violates that equation. I mean, that's at least what my mathematician friend told me. So this must be a Clang bug, right? Well, if we dig even further, we can find further hints. At this point, we might feel like detectives in some sort of weird crime scene. So we can find some defect reports from more than 2 decades ago, where people asked about this part of the standard. Some of the terms are different here, because at that time, it wasn't called an indeterminate representation. It was called an indeterminate value. But so what the answer to this defect report says is that these indeterminate values can change if you look at them multiple times, basically. So it's a valid value, but it's like not always the same valid value. And the implementation, another part of the answer clarifies, is allowed to treat indeterminate values as being different from any other value, even though the standard also says that they are valid values. I don't quite know what that means, but the typical interpretation of that is that we kind of think of x kind of being unstable, and so each time you look at it, you get a different value, and that's how you can kind of violate this assertion. So I guess that's the answer then. So if you look at the IR that Clang generates here, it actually gives this program full UB. There's like a no undef annotation somewhere. So I don't think that is backed even by that part of the standard. But this aside, just figuring out the behavior of this program, what are the legal outcomes of red from the standard is really, really hard or nearly impossible. You kind of have to dig into these old defect reports, which are not normal, like they don't apply to today's standard. This is a defect report for a 2-decade-old standard. The standard hasn't really been changed in that regard. So this is really tricky. And to be clear here, I don't want to throw shade on the C standards work here. They are doing an amazing job at something really hard, which is a very advanced form of cat herding, of getting a whole bunch of compiler developers and implementers together and kind of getting them to agree on many things, which is non-trivial. And they did many things right, and they have this extensive standard, much more detailed than what we have. But they also made some mistakes, which is not too surprising when you do this kind of work. And I would like Rust to ideally not repeat those mistakes. I think we can make our own new and fun, unique mistakes. So that's what this talk is about. So when we get to a Rust language spec, there are some Desiderata I would like to propose we should kind of measure. We should expect the spec to have or to be successful. And in particular, I would like it to be precise. There should be like in some mathematical sense, there shouldn't be any room for ambiguities in the specification. So we don't have to do this kind of guesswork that we just had to do interpreting this other program. And actually, I would go one step further. I would say the spec should be executable. So over the past decade or two, there has been a bunch of academic work specifying complicated real-world systems. For example, we have a very detailed machine-readable formal specification of a very, very large part of the ARM instruction set architecture at this point, actually generated from the official ARM documentation. It's really impressive work. And part of the lessons one of the lessons we learned as part of that is these specs themselves, they're huge artifacts, and we need to be able to test them. Because otherwise our spec is going to have bugs, and then, I mean, what do we do with that, right? So we need to be able to test them, and for that we need to be able to run them. Just take an example, and here's the expected output, and just make sure the spec actually says what you want it to say on these examples. And that's also super useful for tons of other things. You can use if you have a question like the example program we had earlier, you can just ask the spec, and it gives you an answer rather than having to read the spec. You can use it as an oracle for fuzzing. Like if you come to compare if your compiler is correct, just generate a whole bunch of random programs and see if it says the same thing as the spec. Executable specs are really, really valuable. And so I think this is an absolute must for a proper spec these days. But also, of course, I would like the spec to be accessible. I mean, we can, like, I'm an academic researcher. We like writing our papers with lots of Greek letters and weird lines in them. And they are amazing, but not many people can read them unless they did a PhD in programming languages. And the Rust spec is something, I mean, Rust unsafe code authors need to be able to read that to be able to write Rust unsafe code. So we can't have that be full of Greek letters. Right? We need to find some way to make this precise and executable while also being accessible to at least reasonably well-experienced Rust developer. I wouldn't expect like someone who's just starting to learn Rust to be able to read this. That's okay. I think it's okay to expect some amount of Rust understanding, but it's not okay to expect a PhD in programming languages. So this is what I'm trying to achieve with this project of mine called MiniRust. It is a core language, we will see what that means, that can fully capture the runtime behavior of Rust programs. And the style of the system is it's what's called an operational semantics. We'll also see what that means. Expressed in Rust-like pseudocode. We'll also see what that means. So let's start with an example. Here's a very, very simple Rust function. It can't be much simpler than that. And here's the same function in MiniRust. So those of you that work on the compiler, MiniRust is very much like mir. So should be easy to parse in that front. We have a function body which has a list of basic blocks. Every basic block a list of statement followed by a terminator. And then whenever we access a local variable, because a local variable is a place where you can store some data, you need to be explicit about what do you want to do with the place. Do you want to load from it? Do you want to store to it? So the typically implicit in Rust place to value coercion is made explicit here. So we load from X, we add 1, and then we store the result in the place on the left-hand side of the assignment. The return value is stored in dedicated return place, which is just another local variable whose name is given up there. By convention, I'm using ret here. This is all kind of fake. MiniRust doesn't really have actual syntax. You can't write MiniRust programs in syntax like that. But I'm just displaying the syntax of the language like that. So to understand what MiniRust would say about our initial example program, first thing we have to do, of course, is translate this program into MiniRust. Now, literally translating that would give us way too much output, but we can use this program here, which is almost the same. So what does this program do? Well, we have a local variable i8, and then the first thing we do is we storage live it. So this is the moment where we just have a local variable i8. This local variable doesn't actually yet have any memory, because by default, local variables are dead. And so this is how we model kind of scopes, right? A variable that only actually exists in some part of the function. So we enter the scope, we call it storage live, and this is a bit like malloc or Rust allocate for stack variables. So we do that, and then we do the comparison, and I've now replaced the short-circuiting OR by a non-short-circuiting OR just to keep the code a bit simpler here. But this is basically the same check as what we did before. And then we jump to different basic blocks depending on the result of the comparison. Okay, so we've seen some MiniRust programs, but those were concrete examples, right? The point of a spec is to say in a finite form something about all possible examples. So we need to find some way to do that. We can't just list all the programs. And so we need, first of all, of course, a proper exhaustive description of the syntax that to even define what is the set of all MiniRust programs. And then, and that's the crux, of course, a description of the runtime behavior of some arbitrary MiniRust program. So to describe the syntax, this is what I would do if I would put this into some sort of PL paper. This is probably not too bad. I mean, some sort of BNF grammar is actually fairly widely used also outside of hardcore PL research. So I would expect many of you would be able to kind of understand what that is. But still, let's already start thinking about how can we make this as accessible as possible to this specific audience, you all, Rust programmers, without losing the precision that is kind of implicit in using some sort of mathematical notation. And so what I'm going to do is I'm just going to simply write Rust code. Or Rust-like pseudocode, which is a subset of Rust. So instead of saying a basic block is like statement with a line, semicolon, term, we just say, well, a basic block is a list of statements followed by a terminator. You can think vec whenever you see list, but I want to keep it a bit more abstract here. And then a terminator is like one of these things, and then we have statements and we have expressions, and we can just describe all of this, basically describe the abstract grammar of the program as Rust data types. So this should be abundantly clear to everybody who's learned like a few weeks of Rust. It's just very basic Rust data types, right? Probably just after the first week already. So basically, in terms of the syntax, we are done because we don't actually care about a concrete syntax. So we don't need a parser or anything like that. We only need to represent the concept of the program. Okay, so now we get to the interesting part, which is describing program behavior. So there are various different kinds. If you went to some lecture at university about operational semantics or so, there's various different kinds of ways you could express program semantics. And what the CSNET does is what I would argue is some flavor of axiomatic semantics. It's not exactly the typical axiomatic semantics, but it's some flavor of that, where basically the standard gives you a whole lot of reasoning principles which you can use to argue for the correctness of your program. And then if you want to say that my program is fine, doesn't have to be, you have to find sentences across the standard which you can chain together to make an argument for why your particular program is fine. And that has various downsides. I mean, we've seen already it can be hard to even find out where you have to chase those sentences across the standard. It's very, very hard for a compiler to argue correctness of an optimization against such a specification, because you kind of have to be like, okay, give me any program that was somehow proven correct by chaining together these arguments, and now I have to think about what I can do with that. But this is super hard, and it's not really how any of the formal approaches for compiler correctness work. And it also can have accidental side effects. I mean, C famously added provenance to their standard, and then 20 years later they realized that they did that. Because it's very easy to add some rules which talk about things like pointers being derived from other pointers or so, and then later you realize, oh, this actually has profound consequences that affect all of the rules everywhere, and it wasn't accounted for. So I think there's some major downsides with this type, which is why I think in Rust we should go for an operational semantics, and it seems the project agrees because we have an official operational semantics team. So this part is kind of already done and decided as far as Rust. So what's an operational semantics? Abstractly speaking, for an operational semantics, you define a state space and a step function. I'm going to make this put this more into Rust terms in a minute. So what we would write formally is we first describe our state space. So that is kind of all of the things you need to remember to describe the current state of how far you've executed the program, right? The value of all the variables, the contents of all of memory, everything. So mathematical notation would look something like this. And then we have a step function, which tells us from one state, how do you compute the next step? How to execute one statement or whatever granularity of step you might choose. And the funny half arrow means that this is a partial function, because a step there can be no step, right? This is a program which has UB. It's often modeled as just you can have no step here. But again, this is mathematical, and if we would start out writing those functions, it would get into Greek letter territory very quickly. So let's avoid that. Let's use Rust syntax. We can just define the state space as here's my struct, and here are the pieces of the state. Here are the things I need to describe the current state of program executions. And I mean, Rust has functions, of course. So if we want to write a function which computes the next state, we just write a function that computes the next state, and it's a partial function. We can do this in Rust. We have this fancy thing called option. And so what this is, you might recognize, is it's basically an interpreter. Right? An interpreter somewhere has all of the state that is needed to track like what is the contents of everything, and it has a function you can call to do one step. Or usually it's in a loop and you just do the entire thing, but you can imagine just extracting the one step thing into separate functions. So an operational semantics is basically just a mathematical version of an interpreter. So what we're going to do for MiniRust, we're going to give it an interpreter. And so I can't go over the entire interpreter here, but I want to take a slightly closer look at this memory type, because that's where some of the most interesting stuff happens. So the memory from the perspective of MiniRust, and now we get into choices I made, some of which are kind of just modeling existing consensus or already decided things, and some of which are just decisions I made so that I have a proposal for what MiniRust could look like, and there's going to be discussions on what the final version of that looks like. So we have the address space of the program, let's assume a 64-bit machine, and just spread across the address space, we have a bunch of allocations. The spec doesn't care about stack or heap or globals or anything. Every allocation just gets some address randomly, non-deterministically, anywhere in the address space. And more importantly, the contents of these allocations are, well, they are the bytes stored inside the allocation, and those bytes are a bit funny, because those bytes can be either the bytes you all already know, standard just initialized to some particular value, or they can be uninitialized. We consider this to be just another value a byte can have. So there's explicit tracking in the interpreter state, which is just the spec, of which bytes have been already initialized and which have not. So this is, of course, a picture. This is not precise and unambiguous. So let's make this precise and ambiguous using the tools we have. Memory is just a list of allocations. An allocation has an absolute address and a list of bytes, and a byte is either initialized or uninitialized. And so even these interesting non-trivial concepts here of what is a byte are very easy to express in Rust, because Rust has enums, which are amazing. And so every Rust programmer understands what these few words here mean, and we've very precisely described a very non-trivial aspect of our semantics in a way that is accessible to everybody who did at least a week of Rust. And so one thing you might also notice looking at this in particular, if you are someone who thought a bit about the C or C++ specifications, is there's no types here. Like, types are very important in Rust, and somehow they are suspiciously absent entirely from this view of memory. Because in this model I'm proposing, types don't actually show up in memory. They show up when you do stuff with the data in memory. So more specifically, types are or define how values as like abstract mathematical high-level concepts are represented in memory. The way we could think about it is there's some enum of types. I won't bore you with the details. You all know the Rust type system. And then there is an enum of values, which is in particular includes things like mathematical integers. Right? At this point, the number 260 is really just the mathematical number 260. It's not like a sequence of bytes or Indianness or any nonsense like that. And then like a Boolean is really just a mathematical Boolean. A tuple is just a value for each of its fields. Like this is a high-level view of the value. There's no bytes anywhere here. But of course, in Rust, we store values in memory and we load them out of memory. So we have to somehow bridge that gap. And to do that, we have two functions. There's an encode function where, given a type, if you have a value, it constructs a list of bytes. And that's basically just a form of serialization. Right? We're given the number 260. We're saying my format is I32. OK, I know it's a big endian system. Here's the 4 bytes that get out of that gets turned into. And then, of course, there is a function which does the opposite. Right? Whenever you have serialization, you also have deserialization. So those two functions together define this abstract concept of like how does a high-level value get represented as a low-level list of bytes. And crucially, decode can fail. Right? It returns an option. So some representations, some sequence of bytes just don't parse. They're just not a valid representation of any high-level value. So if we want to discuss our example now, we will get into, well, there was a type I8, is the type I used there, right? So we want to answer the question of what exactly happens when we decode an I8 from its representation. And so slightly simplifying here, we're only given a single byte because I8 has size 1. And we have to write this function. And so, of course, the first thing you do is you match on the byte, because what else could you be doing? And now, we defined bytes earlier, right? There's two cases to handle. Either the byte is initialized. In this case, well, I mean, there's a bit of stuff going on here. We have to take the byte and do the 2's complement to get the mathematical integer. Details don't really matter. The point is, this is something you can define. And everybody agrees on what should happen there. More interestingly, there's also the uninit case. You can't just forget that. Right? If you didn't write this, Rust would just not compile this code, and neither would our Rust-like pseudocode. And what we do is just return none. I mean, we could also say return 0 or something, but that sounds pretty bad. So we just say, yeah, if the byte is not initialized, then this is just not a valid representation. And so knowing that, let's get back to our example program. And let's see what happens when we run this program in the MiniRust interpreter. So the first thing that happens is storage live. At this point, we create a new allocation that backs the memory for x. And initially, well, it only has a single byte. And that single byte is initially, of course, uninit. That's the entire point of this uninit special magic value. And then we go to the next line of the program, where we load from x. And so what happens, where we take this uninit byte and we pass it to the decode I8 function we just saw. And that function returns none, which is an error. And so at this point, the specification says we have undefined behavior, because whatever you did there, whatever you gave me there in terms of memory, is not a valid representation of any I8 value. So in the spirit of being executable, I can show you this as a demo. So here, no, I want to increase. Here we have, again, as a Rust file, just the program that I used. And if I run this in Minitest, our caching isn't perfect, so there's a bit of rebuild going on. And then first of all, we see that the Rust compiler is way too smart and already recognizes that something is wrong with the program. But then at the bottom here, we have the output from the MiniRust interpreter. This is not the most beautiful output. The interpreter is not meant to be as a user-facing tool to find bugs in your code, right? It's meant for us to find bugs in the spec and to do conformance testing and things like that. And we will work on improving that, of course. But nice error messages are like the last priority in this particular project. It's not Miri. But the key point is that we could just run the spec, and the spec immediately told us unambiguously what is the answer to the question of what happens when you run this program. And the answer is it has undefined behavior. Okay, so beginning to wrap up here, we've seen how the MiniRust formal specification, which is basically an interpreter, is able to precisely capture why this program has UB. And roughly the high-level structure of MiniRust is that, first of all, of course, we have to translate the Rust program into MiniRust. The details of that are TBD. Of course, at some point we need to make that formal as well, and we will think about that at some point, but not yet. And then we have a MiniRust program. We have the MiniRust interpreter, which is written in this Rust-like pseudocode that is called specker. And you can think of it as basically a purely functional subset of Rust. And you can just run that as you just saw in the demo, and it'll tell you what the program does when you execute it on the specification. So I have a bit of time, so I want to show you at least one of these aspects here of MiniRust, which I find interesting, or one of the consequences that happen. So one of the types, of course, we have to define is bool. So this is the decode function for bool, right? Again, bool has size 1, so we take a single byte. If the byte is initialized to 0, then this represents the mathematical Boolean false. If it's initialized to 1, mathematical Boolean true. Everything else, not a valid representation of a bool. And so one of the interesting things that happens here is that if you try to parse like 55 into there, you also get none. Right? So all of these things, which we often call invalid representations, that's also kind of defined as part of this. So if you go to the reference, and there is this section there on like it's UB to construct an invalid value, then we list there, well, a bool must always be false or true, 0 or 1. And this is already captured as part of this, right? So the main goal is to define how do representations relate to high-level values. But actually, as part of this, we are implicitly defining the validity of the language invariant of the type. That invariant isn't actually a part of the semantics. It's just a derived notion from the fact that some representations are not valid. And for all the others, we have to define what the value is. And then if we have a fallback case like this one, we just say, OK, everything else is invalid. And I have one more here about padding. So this is the idea here is if we have a type, like let's say we have a pair with 2 fields, and there could be padding in between those fields, how do we encode and decode that? Well, what happens here is for decoding, we just subslice the corresponding 2 parts of, like we get a large array of bytes, and there's like 2 subslices which correspond to the 2 fields. We just decode them, right? What else would we do? But in particular, this means if there's padding between the 2 fields, it gets entirely ignored by this decode function. It's not even like the value we return here, the pair, doesn't even have that padding in it. It's just lost. And then when we encode, we start with an array full of uninitialized, and then we just slap the 2 encodings in the 2 places. So there's an interesting quick quiz question here, which is if we start with a whole bunch of zeros, right? We have 4 zeros, and then we decode that and encode it again. So we round trip from the high-level value to the low-level representation and back. At this type, I8, I16 with a defined field layout. So there's a byte of data, then there's padding, and then there's 2 bytes of data. What happens? And the interesting thing that happens is that the padding gets lost, because when we decode, we just get the mathematical tuple 0, 0 as a high-level value. And then when we encode that again, all of the padding is reset to uninit, right? Because the fact that there was a 0 in the padding is not even represented. So these decode-encode round trips can be lossy, and so these representation relations also implicitly define the fact that padding is lost on typed copies, as we say. The encode-decode round trip, by the way, has to exactly preserve the value. That's important. OK, so the MiniRust interpreter, again, the goal is to precisely capture for any program, whether it has UB or not. And I should also mention that this is worked by much more than one person. I have a lab now, so I get to assign students some tasks, and they will happily do it because they get credit points for it. So a whole bunch of people worked on various aspects of MiniRust. In particular, Rudy did all of the work of making MiniRust something you can actually execute, not just a whole bunch of markdown files. And then a sequence of mostly bachelor students added a whole bunch of Rust features. So at this point, we are fairly close to covering most of Rust. On the other hand, of course, there's still a long list of things we don't have. I don't know if we will ever get floats. Probably at some point, someone will get nerd sniped into doing that. But there's lots of intrinsics we need. And to make this practical, to test the spec on slightly more interesting programs, we also need to do about some engineering things. And of course, we want to make it formal with a connection to the ROX prover or to Nico's Mill formality project. So there's a lot of work still left to be done. But yeah, I would like to add at least moving towards 100% coverage emoji to the list. And there's one final emoji I want to add here, because currently this is my project, my research project, and it will stay like that for a bit more because I need to complete it first. But I hope long term we can all work together to make this part of the official specification for Rust, to make it authoritative. That's what the final emoji is meant to represent. Because in doing that, we would make Rust, to my knowledge, the very first language that, of its level of complexity, a language that has undefined behavior programmers have to worry about with unsafe code, that actually has a mathematically formal spec officially in its standard. And I think that would be an amazing thing for us to do. So thanks a lot.
Thank you, Ralf. Okay, we have a few minutes for questions. Wow, okay. I'm going to go this way.
Thank you very much for your presentation. My question is, you showed this really nice operational semantics with the step function. In the state that you presented there, the state struct, you also had a list of threads. What happens when threads are introduced in this model? Because then you have some non-determinism there, probably. So does the step function turn into something more complicated than going from state to option of state? Or what happens there?
Yes, yeah, very good question. Yeah, so the language spec is non-deterministic, and I cut out the slide that explains that for lack of time. So the short version for the experts is we do a monadic representation of non-determinism. So the slightly longer version, well, the slide is cut, so I can't really show it. But basically, in the so Specker is a language. It's a purely functional subset of Rust, and it has one or two really extra funny operations. And one of them is pick, which is a non-deterministic, which is meant to model non-deterministic choice. It's a function where you basically give it a type and you say, give me some value of this type. It's slightly more refined, you give it a type and you give it a predicate, which is a function from the type to bool, a closure from the type to bool. And the pick function is specified to just be non-deterministically return any value of the type that satisfies the predicate. And so when we execute the spec, of course, we can't, so nominally what happens is kind of the program branches every time you use pick. And all of these executions now could happen. And if we did a formal proof, we would have to worry about all of them. Of course, when we execute the spec to test it, we will just pick one at random, because that's the best we can do. It's an easy word. You could imagine some fancy symbolic things or whatever. But basically, we have this very special magic function, and we call it in the spec at all of the moments where we want to model non-determinism. And then the executability is slightly degraded there, but the mathematical rigor is still there. If we translate this into a formal model in Rock or anything, we can use an actual accurate model of non-determinism. And yes, I mean, it's a bit less accessible because it's a weird magic concept, but non-determinism is something we will need. So I think this is a reasonable, and also it's formally a very common way of exposing non-determinism in a specification like that.
Okay, I think there was just one over here.
So you showed that in MiniRust a byte is either an init or an integer value. Where's the provenance?
I removed it for this talk.
Okay, thank
you. Yes, I didn't have an hour, so yes, there's of course also provenance actually in those bytes.
On the subject of pointers and references, if memory is bytes, how does that at all? How do you enforce the aliasing model?
Yeah, the answer is provenance. So again, it's something I didn't get into explaining here, unfortunately. But a pointer is not just 64 bits. A pointer is a 64-bit address plus some magic extra metadata called provenance. That's the high-level-ish mathematical value of a pointer. And then of course you need to be able to encode pointers into memory and decode them again. So we also need to enrich bytes with provenance to be able to round trip this. And then using provenance, we can basically track which pointer got derived from which other pointer. And we can use that for the aliasing. So the MiniRust that I just executed, I showed you, it has an implementation of tree borrows already inside of it. So it does do all the aliasing checks.
Okay, I'm very sorry to the other 45 people or thereabouts who had hands up, but I am sure Ralf will be very happy to talk about this later.
Definitely.
We are unfortunately out of time, and so thank you again to Ralf.